Section 3.2, the product topology. Definition 3.6. Let X and Y be topological spaces, and X times Y be their product as sets. And the product topology on X times Y is the topology generated by the basis B of products U times V, where U is an open set in X and V is an open set in Y. Okay. The resulting topological space X times Y is called the product space of X and Y. Now, to be careful here, this is not saying that the open sets of X times Y are products of open sets in X and Y, right? If you want an open set, it's just saying that this is a basis for the topology on the product space. So if you want an open set in X times Y, you have to take an arbitrary union of products of open sets. Okay, and that gives us something reasonable. So let's look at exercise 3.13. Let X be PPR2 at 0, 0, the particular point topology on R2 with the origin serving as a particular point. Is X the same as the topology that results from taking the product of the real numbers with itself, where each R has the particular point topology at number 0? Justify your answer. All right, well, when I started working on this one, I actually thought it was going to be true, but it turns out it's not. One of the topologies is a proper subset of the other one. Okay, so let's show this. The topologies are not the same. Consider the set A consisting of just 2 points, the origin and the point 1, 1, which is open in this particular point topology on R2 at the origin. I've illustrated this set here in R2. You see it just has these 2 points. It's open in this particular topology because, well, it contains the origin, right? That's all you need to do to be open in that topology. Okay. So I want to prove by contradiction that this set is not open in the product topology. Okay, so suppose for a contradiction that A is open in the product topology on R times R, which is the same thing as R2. Okay. Whereas in the problem, each copy of R has the particular point topology PP R sub 0. All right. Well, if that's open, then one thing that means is that there is some basis element in the product topology, right? So some U times V of this product topology such that, well, it contains the point 1, 1, right? And moreover, is contained in the set A. Okay, so it doesn't contain too much more, right? Because A only contains 1, 1 plus the origin. Okay, so that's one way of stating what an open set is. If you take any point in it, like 1, 1, then you can find a base element which contains that point and is contained in your set A. All right, well, this is going to be trouble because this implies that, well, U and V must both contain the number 1, right? If the first coordinate here comes from U and the second one comes from V. Okay. And, all right, but this is a base element, and remember, base elements, the U is open in X and the V is open in Y. So what that means for us is that, well, the U and V here must both be open in the real numbers with this particular point topology at 0. Okay, So in order for U and V to be open in PPR sub 0, they must both contain 0 as well. Okay. Well, but they both contain 1 and they both contain 0. That gives us some more points that have to be in the product. Right, then 1, 0, and for good measure 0, 1 are also in U times V, contradicting the assumption that U times V is a subset of A, right? Which it wasn't an assumption, I guess, but it was a result that we already had. Okay, because indeed these points that must be in U times V, they're not in A, right? A only had the origin and 1, 1 in it. So we have our contradiction, right? The product of sets containing 0 and 1 would have to have these other two sort of vertices of the square here as well. Okay. So we found an open set in PPR2 at the origin, which is not open in the product topology of these two copies of R. So these topologies are not equal. However, the containment does hold in the other direction. Okay, the product topology here is a subset of, or in our other language, we can say it's coarser than the PPR2 at the origin topology. Okay. So this would be interesting for us to show as well. Well, let's see. We take a basis element U times V of our product topology. It must have U and V each being open in PPR as 0, right? So each containing 0, or they could also be equal to the empty set. Okay. I didn't have to worry about that up here because I knew that U and V already contained something, so they weren't empty. All right. Well, then it follows that U times V either contains the origin, right, if both U and V contained 0, or if either U or V were the empty set, then their product would be empty. Okay, so or is empty, that's the other possibility. But in either case, that product U times V is open in our PPR2 at the origin topology. Okay, so I've shown that any basis element of the product topology is open in the PPR2 at the origin topology, and therefore any open set in the product topology is going to be a union of these open sets and will be open in the PPR2 at the origin topology. So we've shown that one topology is a subset of the other one, but the reverse containment does not hold, so they are not equal to one another.